Well, we hope for you guys to be okay. Today we are talking about the 6 common mistakes in IS that can be made. We will start our webinar in just a minute. So we do as usual. Bob, you start the presentation.
You bet.
Okay. All right, let me do like this. Request remote control, request. So let me see if it works. Always some delay, huh?
Yeah, technology is wonderful when it works.
Yes. Well, you had the space shuttle, whatever there. You went in the space the other day. You guys are, awesome in the US. Well, Bob, as usual, I don't seem to be able
No?
to give up the remote control. I'll let you control it. So let's go to next slide.
All right.
And next. So before we start, I'm introduce Bob to you guys. So for those who have not met or heard from him before in our previous webinars, Bob has a long career, but he's not that old. My age, right? and he's our guest speaker for today. He has over 30 years of experience in the EX world, and he's a CompEX instructor as well as an instructor of the ICEX CompPC scheme. So both of the scheme out there, and he's also an inspector and a member of the US UL STP committee. Through his company, Source IEX, he's been working in the IEX domain for forever, right?
A long time.
So he has an extremely wide experience, and we'll introduce you to some real problem that he has encountered in his inspections. But before we let him talk, I need a few moments to talk to you about GMI, who we are, what we do, and why we do it. We are a safety company. We manufacture safety components such as interfaces, IS interfaces, and SEAL interfaces designed for automation packages such as TCS, CSD, fire and gas, marine, and so on. And they are used in majority in the industry, most likely in oil and gas and petrochemical, but also pharmaceutical, food and bev, and so on. We have over 40 years of experience, and we are very proud to manufacture our product in our state-of-the-art facility near Milan, Italy. We have a global presence around the world. And because we are a safety company, we try to make high quality safety components because our interfaces provide for the safety of your plant. So we use state-of-the-art technology. We have 100% traceability of all from the incoming components and the outgoing product. So we know exactly who manufactured, the test result, and so on. We have 100% testing on every single device through our automated manufacturing process. We are RoHS and REACH compliant. Now we have, I forgot, there's a new one, skip to ship. You need to register your product. And we have functional safety certification, functional safety management certification up to SEAL3, SC3 for our company as well as our product. And we make safety products because we care about the environment we live in and the people that work within our companies we supply to. Let's go next. So these are the products we manufacture. We have IS barriers. We have safety relays with and without line monitoring. We have isolators, also SEAL certified. We have a series of power supply, EX and SEAL rated. We have multiplexer, temperature multiplexer, digital multiplexer, HART multiplexer. We manufacture a wide range of termination board to interface with the DCS, CSD system in the market. We have a line of SPD or surge protection device. We have some indicators, and we have a training and services division that runs training and services in the EX and SEAL domain. Next, Bob. Okay, we are present around the globe with 10 direct offices, subsidiaries. We have many distributors. We are about 200 people in GMI, and we run a lot of courses. Now we need to change this slide. In 2020, we run very few courses live, but although we have started now running online courses. And with Bob, next year, we will also start some courses on EX. And we have thousands of installations around the globe with our customers, which are system vendors from ABB to Yokogawa, EPCs, many EPCs, we've done many projects with them. And we are very proud to supply to many OEMs on their drilling machine, compressors, skids, wellhead packages, and so on. And we are in the AVL of many end users. I believe next is, okay, here we go. So Bob, I'll let you introduce the subject, but before you do so, let me remind to our guests that there's only one way you can get in touch with us is through the question and answer box. You can type question in there, we'll try to answer them through the presentation or at the end of the presentation. We have received some questions already, and we have prepared a question and answer presentation as well. Okay, Bob, it's all yours.
All right. Well, thank you, Paulo. I appreciate it as always, and thank you very much for joining us today. We've done this quite a few times, and it's a very interesting topic to discuss. The good thing about intrinsic safety is when we do intrinsic safety installations, a lot of the regulations all around the world, no matter where you're at, a lot of the fundamentals are all basically the same. So if you were doing an IS installation design, if you will, here in the United States, we follow the National Electric Code. If we're doing it up in Canada, we're following the CEC. In the international community, we have some international standards. And again, the good thing is, the positive thing is that if you understand how to do intrinsic safety in certain parts of the world, there's a lot of similarities. There are some differences, but for the most part, the installation, the design concepts are basically pretty much the same worldwide. So what we follow as far as standards are concerned, and it's important to understand these because depending on where we are in the world, we have to follow obviously whatever particular wiring regulation standard. Again, in the United States, we follow the National Electric Code, the NFPA 70. Chapter 504 is all the information that we talk about for the installations and design of IS systems. We also have a UL standard that's just recently been published for inspections of EX installations, for zone installations. In Canada, there's a couple different documents, but the CAN-CSA is your intrinsically safe systems document. On the international side of things, we have a couple different IEC standards in the 60079 that we follow. The -14 is a great standard to basically get your hands on and be familiar with. This is the -14 standard is very much the basis for a lot of the competency programs. So if you really want to understand the various programs like COMPEX or the IEC EX COPC program, the -14 is pretty much the benchmark what we use as far as training and assessment. There is some information on design of EX installations as well as IS, which is included in there. The -25 standard is the design of a complete IS system. So now we're talking about taking all of the components that you might find in an intrinsically safe system and putting them together. The -17 is our inspection of EX installations, which include IS. And of course, in Europe, we take the EN versions of the 60079 standards and we apply those. Some other standards that do apply, some of the functional safety standards, the 61508, 61511, those certainly, when we talk about functional safety, it applies as well to intrinsic safety, but there's some other standards as well out there. The American Petroleum Institute is very active, and you'll see their recommended practices show up in offshore installations all over the world. The 14F and the 14FC are design and installation standards for offshore oil and gas operations. And then, of course, the IEC 61892 standards specifically deal with mobile and fixed offshore units, and the -7 is specifically around hazardous locations. So again, this is just representative. It's not all encompassing, but these are the main standards and regulations that really address IS in some way, shape, or form.
Well, Bob, you
We have
mentioned
a
a
first
lot of
poll
standards.
question. Yeah,
So we
already.
are going to ask you guys now, if you have been listening, what is the international installation standard recognized for the installation design of the IS system? You have a way to, there's a poll here. It's we're not judging anybody. Just click on the one you think is the most appropriate. I imagine by listening to Bob that a lot of them have to do with IS, but international standard number one, we have to consider in the question. And I mean, that is a giveaway, no, Bob?
It is a little bit, but
It's the first
what
time
I
I noticed.
consider, what I consider international and what you consider international are maybe two different things.
Yeah, of course, different international. Yeah.
So
I would argue international means something that covers
the globe. Yeah.
All right, so we have, let me end this poll. Let's see what happened here. Share the result with you guys. So most of you have answered I66079-14.
And I would agree. There is
awesome.
Yeah, the main one that we really want to try to follow, and then I guess the -20. You could argue the -25 is also very important. Although the tricky thing is, I did write down EN, so that really applies strictly to Europe. But the IEC version of the 60079-25 applies.
But I can see, we were discussing international, and most people call it because NFPA, it's a national code, so as
That's right.
CSA. All right, great. Stop share is the result. Bob, it's all yours. Continue.
All right, let's close that and we'll move on. Okay, so that slide we already saw. So first off, a little bit before we get into 6 common mistakes, let's talk about what an intrinsically safe system is. I assume most everybody understands a little bit about intrinsic safety, but what people sometimes fail to remember is intrinsic safety is truly a system concept. As a matter of fact, when we talk about IS within the training and assessment programs, we do mention about IS as the only true electrical protection concept, if you will. When we talk about other protection concepts, they're usually mechanical, but IS is an electrical concept, protection concept, and it is a system concept. It's not a standalone. We have to take into account all of the individual items that are part of our intrinsically safe loop. So typically we have our control circuit, we have our associated apparatus, we may have some sort of junction box, and we of course have our field device. And we have to look at our entire system to make sure that they're matched, that everything works, that we're below the minimum ignition curves of the particular gases and vapors that we have in the environment. So the associated apparatus is really where we kind of focus our attention on. That is typically referred to as an intrinsically safe barrier. But again, we have to look at cable, the field device, and our control circuit as part of our entire loop. So there are 2 different kinds of associated apparatus, not brands, but types, if you will. The one on the left-hand side is a galvanically isolated product. The one on the right-hand side is a Zener product. These are 2 of the devices that you would see commonly in industry. The way you can kind of tell how a Zener barrier, the difference between the 2, if you'll notice on the Zener barrier unit, you actually have some sort of little earthing tabs, which is generally a dead giveaway that tells you just by looking at it without looking at the labels. That's generally a dead giveaway that's telling you that you're looking at a Zener barrier versus a galvanically isolated barrier. So how they work. A galvanically isolator is made up of a bunch of components, and this is true for every manufacturer, regardless if it's GMI or whomever else it is. But basically, what you have a current limiting resistor, you have a transformer protecting fuse, and you have a safety transformer, and then basically you have some Zener diodes. So if you have a fault condition come down through from the control circuit, what'll happen, it'll hit the safety transformer. It should be isolated. It's galvanically isolated by the use of the safety transformer. The transformer, in effect, is basically mimicking the signal, if you will, to the field device. And it's this constant back and forth between the safety transformer with this signal. And it sits there. It's an active device. So it does need to be powered. It is loop powered. And it will basically send that signal back and forth, back and forth, back and forth, and it will provide protection downstream. Now, under a fault condition, a galvanic isolator, what happens if we have a fault, generally speaking, it's going to be coming from the control circuit at that particular point. When it hits the transformer, either it potentially could blow the fuse, but generally it's going to stay in the safe area. It will basically, through the use of the transformer, keep any fault condition from going into the hazardous area. So we're more or less at this particular point in time completely protected, because what will happen, it will either blow the fuse, the resistors may turn on, the Zener diodes could turn on, but more or less the transformer is the main form of protection. The important thing to note here is that a galvanically isolated product, there is no need for a safety ground under a galvanically isolated type product. Now, the Zener barrier concept is similar, except if you notice that we don't have, in this case, a transformer. So we still have a lot of the same components. We have a Zener protecting fuse, a current limiting resistor, which is a fail-safe type resistor. And then again, we have voltage limiting Zener diodes. So if we have a fault condition in this particular situation, what happens is Zener diodes start to open up, and they allow any excess voltage to be transmitted to a ground. And if you notice down on the right-hand side, you have to have a nice ground, a good ground connection with at least 1 ohm of resistance, no more than 1 ohm resistance to earth. Notice that that is a separate earth from your normal dirty earth that you would normally find in a lot of your facilities. So we have to have that nice, clean earth, if you will, to make sure that we shunt any excess energy to ground. Now, Zener barriers are basically, unlike galvanically isolated barriers, these are passive devices. They just sit there. They are not loop powered. They just sit there and they transmit. The signal just basically passes right through it, back and forth, back and forth. So it doesn't really come into play until we have a fault condition, and that's where everything kicks on, either the fuse, the resistor, or the Zener diodes. Now, the important thing to note is under a fault condition with the Zener diode, we can have a situation where potentially, depending on how this is wired up or miswired, we could have a fault condition in a hazardous location. We could have either our earth connection improperly tied. Maybe we don't have a standard good ground clean earth. Possibly we could have a fault condition go to the dirty earth in the hazardous location. So this is where we get into issues with grounding of Zener diode barriers. So this is one potential issue that we do run into with use of Zener diode type products. So this is probably the biggest drawback that we do find with the use of Zener diode products. And of course, one of the big common mistakes is the fact that we don't have, in effect, a good clean earth. So this is the situation that we do not want to run into.
Wow, great, Bob.
We have another poll question.
Another poll question. Let me launch this poll, you guys. What device can typically be installed in conjunction with an IS barrier? Is it a EX light fitting, or a transmitter, or a motor, or a simple device? Or B&D meaning transmitter and simple device, or none of the above? Let's see, guys, what you think. I started the poll, right? Yes. Be able to see it is not a difficult question, because IS barrier have one limit. Let's say the limit is power. You know, to make something intrinsically safe, it must be inherently safe. So when you have a lot of power, you know it already. When you get hooked up on a 110 or 220, changing your light bulbs or doing some work at home, you know, that's a jolt. Cannot make that safe. All right, we have a lot of different questions though today. I would imagine we need to review this issue a little bit.
Yeah.
Anybody else? No, they're okay. Let me end the poll and I'll look at some questions that are coming in. And share the result. Bob, I'll let you comment while I look at these questions.
Yeah, and this is not to see the wide range of answers. It's not uncommon. A lot of people perceive that I can use intrinsic safety in a lot of different applications, but it really is limited to low energy type applications. So things like light fittings and motors, generally speaking, now there are some components that we could find within an EX light fitting that are actually intrinsically safe, but generally speaking, an EX light fitting is not using IS as its protection concept. And certainly motors require a heck of a lot more energy, if you will, that is above the minimum ignition curves of what we typically would find with an IS barrier. So generally speaking, the correct answer would be things like transmitters and simple devices. So the correct answer would really be E, right?
Sorry, E. Yeah, you're right.
Yeah, yeah.
Okay, stop share and let's move to the mistakes now, right?
Yep, absolutely. We'll get into the mistakes. And we see some questions, and we'll get to those questions, I promise.
Yeah.
So the first mistake, I already kind of mentioned this to you, Zener barriers require, to work properly, require a dedicated earth. So again, in many instances, the clean earth is attached to the dirty earth, or in some cases, the Zener barrier has no dedicated earth. So I was doing an inspection with a client here about 3 weeks ago, and we saw an awful lot of Zener barriers in their installation. And of course, we opened up the panel, and I noticed that there was no dedicated earth. And I brought that to their attention, and they said, "Oh, well, we didn't think we needed to." And I said, "Yeah, you pretty much need to." So
That's called you grounded it though. I've seen installations where there's no grounding to the Zener barrier.
Yeah, there was actually no grounding whatsoever. It wasn't as if they tied it into normal earth. They didn't tie it into any earth whatsoever. So in this particular application was for a ship, and grounding things on a ship is usually an interesting scenario, because where do you tie it into and keep it separate from the clean earth? But anyway, again, no more than 1 ohm resistance. So this is generally the first thing when we're going in and we're doing a detailed inspection on IS. We want to look for that clean earth, and we want to measure it. We want to see it. This is the other issue that we do find when we're using Zener diode barriers. A lot of people will mount them onto DIN rails, which is perfectly fine. But then they fail to remember that, generally speaking, those DIN rails are metallic. And if those metallic DIN rails are attached directly to, say, a metal enclosure via non-insulated knockoffs, then we're tying it directly into the dirty earth. So the important thing is to remember is that we want to make sure that we're using insulated standoffs, if you will, to our DIN rail when we're using IS Zener diode type products. So they must be isolated from the enclosure at that particular point in time. If we're looking over there, if you notice on the right-hand side, that's just an example of what you would typically find. And notice that we have both a clean earth and a dirty earth that we are typically tied into. So we just need to make sure.
Remember that, isolated barrier, the main advantage of an isolated barrier is they do not require this safety ground.
That is correct. That's the main reason why many
big mistake.
Yeah, that it eliminates that mistake, or that eliminates that issue by using a galvanically isolated product. Okay. The other issue is the second mistake is that there's a requirement, and this requirement is pretty much in every standard around the world. There has to be a segregation between intrinsically safe and non-intrinsically safe circuits. And that distance requirement is 50 millimeters or 2 inches. Now, in this particular installation, what you see is that these are strictly just intrinsically safe circuits, if you will. And we can tell that from blue terminal blocks. There doesn't seem to be a combination of power and intrinsically safe within this one enclosure. And of course, we have cabling that's generally blue or marked intrinsically safe or tagged in some way, shape, or form. But again, there's no exposed conductive parts of the wiring. What you see on the right-hand side is perfectly acceptable. Now, right now, everything looks good on the inside of this enclosure. So we have power coming in from the top. They are being fed into the barriers. And then we have our outgoing blue cables coming out of the intrinsically safe side of the barrier itself. But then what happens is that somebody comes in and says, hey, we need to do some rewiring of something of this. So now all of a sudden we've done a service loop on the inside of our panel, and now we're starting to wrap around individual conductors. So this is another fault. We want to make sure that we're keeping this 50 mil separation between our IS and non-IS, not only in things like cable trays and outside of the panels, but make sure that we're doing it inside the panels. Now, there are some ways that we can get around that 50 mil requirement when we start using shielded cables, when we use armored cables. Certainly, we can run instrumentation cables in the same trays as long as we have that either the 50 mil separation or we're using shielded or armored cables. Or in some cases, we can also use partitions. So there's different ways to kind of minimize that 50 mil separation, but we do have to keep that in mind in our installation. And the reasoning why we want to do this is that we're concerned about the inductive currents that could travel from a non-intrinsically safe circuit into our IS loop. And that's excess energy that could go above and beyond what our calculations are to make sure that it's still safe and within its parameters. So here on the right-hand side, this is a simple situation where we have a single IS barrier. Notice that we have that IS circuit that's coming out from, or the output on this particular unit is coming up and over, and we have the incoming power going into the barrier itself. Again, everything is fine at the barrier side, but then all of a sudden we bring our cabling right next to each other. So we've now defeated, again, that 50 mil separation, that segregation. So it's important that we understand that we generally are going to want to keep everything IS and non-IS in separate ducts on the inside of our panels. Make sure that we have that nice clean separation between the two. So over on your left-hand side, we see a bunch of IS terminals on the top, and we see a bunch of non-IS terminals on the bottom. We have some nice ducting there that's going on, and we have this nice separation between the two. We have labelings. We show all this good stuff. Everything looks fantastic on the left-hand side. Now on the right-hand side, what you see there is on the inside of a flame-proof panel where we have a couple barriers. And what you actually see here, and I see if I can annotate this and draw, what we actually have over here is that we have a contactor, and then we of course have our IS barriers over here. And then they've put a partition right in between the two. And that was to give us our 50 mil separation between here and here. The problem is that we have now taken this cable, and these cables are less than 50 mil. And unfortunately, these are potted and sealed barrier glands that have actually already been poured and installed. So this was an installation that as soon as I opened it up and I looked inside the panel, I realized, oh no, this is not good, because they're going to have to disassemble these glands, re-terminate it, and make sure that they run it in a way that maintains that 50 mil separation. So we want to make sure that we keep that in mind. We do all that good stuff. Make sure that we keep a separation. So that's mistake number 2. There's another example where we have some power cables and some IS where, again, when it comes from the manufacturer, everything is fine. We have a separation between the two, but then as soon as it gets out into the field, we start doing all this looping. And put all these service loops, and now we have defeated the whole purpose of maintaining that separation.
All right, well, so we have missed, oh, what did I just do? Okay, we have a poll for you guys. We have mistake number one, which was grounding, not grounding at Zinabere. Mistake number two is keeping the right separation. But how much? You mentioned this number, I don't know, at least 20 times today, just before now. So you guys cannot make a mistake here. We need to keep separate IS and non-IS. In fact, in doing that, I will also answer a question. The question says, can IS circuit cable and low voltage cable be run side by side? As long as both are SWA cable. Not sure what SWA means.
Yeah, so steel wired armored cable. So yes, if say, for example, you're running steel wired armored cable in cable trays, typically you're not going to have the wire armor on the inside of a panel, but on your cabling going outside of the panel, absolutely. If you were running steel wired armored cable, generally speaking, that's considered to be enough of a shield to protect the IS from the non-IS. So you can run those right next to each other without the need of a partition, excuse me. So yes.
Let's end the poll here, and I guess a good majority of you, 80% answer correctly, 50 mm or 2 inches is the right number. We have other questions, but we'll get to those later.
Yep.
For example, the question about whether select galvanic or Zinabere, we have in the question and answer Cons and Pro or both, so we'll discuss this later. Okay.
Yeah.
And other questions.
And one other thing about cables, since the question was steel wired armored cable, one of the things that we cannot do is that we cannot run IS and non-IS within the same cable. That's an important thing to remember, right? So even though we might have like twisted, shielded, paired cables, a multi-conductor, multi-core type cable, we can't have IS and non-IS within the same cable. But running them next to each other is okay as long as one of the cables has shielding or armored. So we can achieve that segregation, again, the 50 mil by the use of partitions. Again, installation and routing conductors are key to maintain the safety. The other thing is where we sometimes see some issues is that notice that we have a bunch of obviously clearance holes here. These are most likely for these cables that are coming here, and of course we have some IS entries that are probably for these cables here. We just want to make sure that we keep this separation. We don't want to have, say, an IS cable gland over here and a power cable gland over here or something like that. We just want to make sure that we keep that separation. It's important to remember all that good stuff when we're doing our installation. And again, sometimes we can go extreme. We can actually have multiple junction boxes where we have some boxes that are dedicated for IS and others that are not. Now, mistake number 3 is no identification of either an enclosure or maybe the cable itself that is telling us that it actually does contain intrinsically safe circuits. It is a requirement pretty much worldwide that any enclosure that contains IS circuits should have or must have some sort of label telling us that it actually does contain intrinsically safe circuits. Now, generally speaking, they're blue labels. There are different requirements as far as what it actually has to say, but more or less, there isn't necessarily a one uniform answer to say, well, it must say this, other than it shall be permanently marked that says that it contains intrinsically safe circuits. So if we notice the box on the right-hand side, we have a nice label on there. On the box on the left-hand side, we see some blue terminals on the inside there, but we don't see anything that's saying that it actually contains intrinsically safe circuits. So we need to make sure that all of our enclosures, our boxes, are properly marked, that they do contain some sort of marking that's telling us that it contains intrinsically safe circuits. We have another poll question here. Yeah, we got a lot of polls this morning.
And I have to get back my live video because I realized I was not on video. Okay, I was trying to type some answers. Wow, okay. Well, you should see the answer coming in fast, but they are misleading. The question is misleading, so you guys should be a little careful, but I can see some of you already made a mistake. Because the question is, all intrinsically safe cable must be light blue. And although, you know, the majority are light blue, I mean, light blue is a preferred color for IS, but is that a mandatory requirement? Well, we have 60-40 answer. Let me end the poll here. 64 correct or wrong? Let's see. End the poll. Share the result. Well,
Okay, so the correct answer is false. Now, it is false in one respect. The standard basically, and this is true for almost every standard that I've seen out there, whether or not it's a US installation, an international application, or what have you. If you are to use color coding as a means to color code your circuits, all the standards basically do say something to the effect of light blue shall be the color that you use. But that's different than saying you must use light blue cable. Because what they more or less are saying is that, look, if you're going to use a color code, then it must be light blue. But it doesn't say that you must use light blue cabling. So the important thing to note is what the standards do say is that light blue is certainly one method that you can use to identify intrinsically safe circuits, but it's not the only way. So some people will actually take some heat shrink tubing that might be light blue, put it over the normal cable. We typically would do that where it exits and enters enclosures. We also want to identify it within the cable trays or cable ladders that we're running at various intervals. Certain standards will say that there is a distance requirement that you must put it. Generally, what I tell people is that just make sure it's visible. So if I look at a run, an IS circuit, I should be able to visually tell that that cable in some way, shape, or form contains intrinsically safe circuits. So again, light blue is absolutely fine. Now, that's what the standards say. However, with that being said, there are times where clients will say, you know what, I don't care, I must have light blue cable. Well, of course, the client can go above and beyond, or you can say, look, I want to use light blue, period, end of story. That's fine. But what the standards actually say, they do give you an out to be able to do it in other methods. So that's the important thing to understand. It does not have to be light blue. It certainly can be light blue.
yeah, it's a good
So
example.
how can we do it? Obviously, we can do light blue. We can put tags on it. We can use conduit where we're putting labels on it. But what we see over on the right-hand side, that's not acceptable. So we just have to identify those circuits as being intrinsically safe.
So Bob, I do have a question. If you go back one slide. So if we use light blue, we do not have to mark otherwise?
That is correct.
Oh,
That is correct. Now, that does mean that we can't use light blue for any other circuits. So if we do use a light blue cable, then we are stuck with intrinsic safety, right? So, and by the way, the question that came up about steel wired armor type cable, that cable that you see, that SWA cable, that's what a steel wired armor cable looks like.
okay.
Okay. And we'll do that and close that and move on. So mistake number 5, incorrect gland selection or incorrect installation. Now, this is not just an IS issue. This is an issue with power, you name it. But the important thing is to make sure that we're using the right glands and that we're installing them in the right fashion. Now, there is a question sometimes that will come up: do we have to use, say, plastic cable glands, or can we use plastic cable glands? Must they be light blue? It's not a requirement that they are light blue, but generally it's good practice, if you will. There are different requirements in different parts of the world with regards to cable gland selection. So I don't want to make too many generalities, but the important thing is to note is that make sure that we select the appropriate glands. One of the things that you will find in the IEC standards is, according to 60079-14, if we have a junction box that contains a single intrinsically safe circuit, we can actually use a non-EX gland as long as that gland meets the impact resistant requirements and all the other requirements as spelled out in 60079-0, meaning that we can basically use an industrial gland for a junction box that's housing a single IS circuit. The moment that we put 2 or more IS circuits on the inside of that enclosure, then it must be a certified gland. So the important thing to remember, select the appropriate glands and install them properly.
Bob, since we were talking about the color, we have a couple of questions might fit right in here. One, I believe I have the answer, but they said I painted the cable dark blue. Will that be allowed? I imagine there's no issue. So.
Yeah, that's an interesting question. It's a question. Is it a permanent label, right? So by painting it, will that maintain its permanence, if you will? And so I would say it could.
Must make sure that the paint sticks.
Yeah, you got to make
for
sure
the life of that.
Yeah, I would, my personal recommendation would be instead of paint, using some sort of sleeving. That would be a better choice as far as I'm concerned. But I'm not saying that painting couldn't work, just to make sure. But we want to make sure that whatever, if we are painting something, is that a permanent paint? So I don't really know the correct answer completely on that one. That's an interesting question. I've never seen it. I'm not saying it hasn't been done, so I don't want to say you can't. I would just make sure that that paint is a permanent paint and it doesn't come off.
What about sometimes you find in the market, in fact, if you look at transmitter, all the IS transmitter are blues, and the question is there anything in the standard about the device? I don't believe so, because for example, IS bearer, you see them in different color, red, white,
Right.
blue, black, and green. So
yeah,
don't think the standard mandates that the product must be wire colored.
No, the field device, there is no requirement that that must be blue. But it is also, you will find the field device, you will find generally, you might find something where it's not a bad practice, because you see some transmitters that can be wired up EXD, and then they can also be wired up EXI. It's a good practice that if you're doing it EXI, well, you want to indicate on the cable if it's EXI, and that's how we're going to tell if that transmitter that might be EXD rated, but it's also EXI. If we have a blue cable or if we have some sleeving, then we understand at that point that we've wired up this particular transmitter as intrinsic safety. The output terminals on a barrier, however, do have to be light blue. So that is a standardized, from the barriers themselves, just the output terminals.
Okay, but one last question here regarding these cable glands. Asking if there is a list of this. Is there a kind of list of cable and correct lamp can be used, this kind of cable? Please mention any reference. I imagine you have to look at the manufacturer,
Well, yeah, the cables themselves, it varies depending on where you're going in the world, right? So, for example, here in the United States, we could be using, for IS, we could use what is called a TC cable. We could use an MC cable. There's all different kinds of cables. In Canada, you would use maybe a Tech 90 type cable, but again, that's not necessarily. Now, cables, generally speaking, for hazardous locations for use in the IEC world, there is a clause in section 9 in the -14 standard, which basically says that the cable should be round, compact, non-extruded bedding fillers, and whatever fillers you have are non-hygroscopic, meaning they don't absorb water. And that's the kind of cable that you would typically use for hazardous locations based upon the IEC standards. What that basically means is that we would use that kind of cable not only for EXI, but we could use that for EXE, EXD, so forth and so on. However, that being said, there are some stipulations because IS allows us a lot more flexibility. We can use, in many cases, based upon international standards, we can use different types of wiring methods. So it's really important to look at the particular wiring regulations in your country to determine specifically what cables you can and cannot use. A couple other things with regards to cable glands. The important thing is that if we notice down at the bottom, we see a cable gland with Teflon tape. And again, this applies to not just intrinsic safety, but any of our EX installations. We don't want to use a Teflon tape between glands and enclosures. We recommend that you use a non-hardening grease. That's what the standard basically says. The thing that you also see, if you see that transmitter on the right-hand side, you'll see the use of a plastic traveling plug. So it's important to remove those traveling plugs before we do an installation. What you see down at the bottom there, you see some little blue plastic glands. That's very common. A lot of people use those. And again, does it have to be a blue plastic EXI cable gland, if you will? Not necessarily unless the client specifically says so. But again, we do have to indicate that it is an intrinsically safe circuit. So by marking your cable with blue sheathing or using light blue cable as opposed to blue cable glands certainly is an option there. And finally, one of the big issues that we find, and this also kind of went back to the same thing on the installation that I had a couple weeks ago, I asked the question for what is called a DSD, and that's our descriptive system document. And a DSD is a requirement for all IS installations, wherever you go. But it's one of the common things that just gets forgotten about. People design IS, they do it, and they put it together. But then all of a sudden, there is no drawing that reflects exactly what was done. So if I'm an inspector and I want to come in and I want to check to make sure that everything is A-OK, I need to have that copy of that drawing to make sure that actually what is out there installed is installed properly and matches whatever is on that DSD. So this is an example of a DSD that shows the devices in our non-hazardous area. It talks about our intrinsically safe interface, our temperature transmitter and RTD, and it'll have all of our parameters, and it'll be basically on some sort of template, CAD template drawing, if you will. So this is really a requirement that we must have when we're doing IS. So what goes on our DSD? This will have our loop calculations, the components that are for use on that circuit, the wiring installation drawings, the cable lengths. And this is one thing that people forget about, is that when we're doing IS, we have storage, capacity, inductance, capacitance and inductance, really capacitance with regards to stored energy. The longer the cable length, the more potential stored energy that we have. So we are limited on IS for our cable lengths, generally speaking. We can't just run between our field device and our IS barrier an indefinite length of cable. So it has to be spelled out on our DSD. What is the maximum length that we can actually have? We should have our unique identification number, and then of course the signature of the designer, and if there is any surge protective devices. And again, the installation must match the DSD. So this is just very briefly going through the information that you would have or need to put together your DSD and to actually select your barriers in effect. So using an example here, this happens to be an intrinsically safe beacon. This will be the information that will be published on the cert for the manufacturer, or it could be in the installation information. So this is giving us some of the parameters that we need to plug in. Then we need to find information on our cable, and there are some default cable parameters, but we could also pull that information from the various manufacturers, and we really want to find our ohms resistance per kilometer or per meter. And then we take our external parameters, and if you notice that they are different depending on the gas groups. So if we're using this particular unit from GMI in a 2C gas environment for a single channel application, we take those parameters. And basically by taking all of this information, then what we can do is plug this into this little Excel spreadsheet that we put together. This is not on the GMI website, but I think Paulo has this and he could send it out, or I could send it out to you. But we basically plug in this information, and everything that you see in yellow is all the correct information that's directly from the manufacturer, or what you've actually put together. And then in green cells is the output. And if you notice down there, it's telling us based upon the parameters with this IS beacon in a 2C environment, using it in conjunction with the GMI Safety D1041Q, along with this particular instrumentation cable, the maximum length of cable is 179 meters. And as long as we stay 179 meters or less, we're A-OK. So this is the information that we would take to put into our DSD. So that's a summary, if you will, of what we actually just created and putting it all together.
All right, Bob.
So,
what are the most common mistakes? We have some questions, so you can go to the next slide, and I will share the question and answer presentation we have prepared for the answers. The question we received through the registration process. We do have some live question here. One specifically ask about whether xenon are isolated. We will get to that soon. How about we answered this in another webinar. It is allowed to use two galvanic isolators, one IS loop to split the signal. It is allowed. There are some rules you have to follow. Of course, you can buy an IS pair which is already designed as a splitter, so you have one input and two output, and whatever calculations are required are done by the manufacturer. Or you can use two devices, but depending if you connect in series or in parallel, the parameters change, right, Bob?
right, right.
You need to calculate. So let me launch the presentation in 1 second, then we get to these questions. There are a lot of questions today. We are running out of time, so well, you might want to look at some of them. All right.
Yeah, while you're that up, yeah, the question on the Excel
share screen. Okay, presentation of PowerPoint. I believe, let me see if you guys see it. Guys, you guys see it? Okay, you see it, right, Bob?
Hold on, I have to get out of my.
I'm not sure I'm sharing or not.
I don't see it.
Okay, wait. Let me. Today is not my best day. Okay. I'm sharing something, but I'm not sure what I'm sharing. Okay, so let me start again. Presentation. Shut this down. Close this off. And share presentation. Hold on 1 second, guys. So in the meantime, we have a big question here on maybe you want to read recording. There's a question on IEC 67914 section. Maybe you want to read it, Bob, because it's a long question.
While you're bringing that up, so the question is in 16.4 states that simple apparatus has to be marked with a durable labeling and can be marked in any way as long as it's obvious that the equipment is simple apparatus. Though the standard further says that simple apparatus does not have to be marked per the normal for EX equipment, so forth and so on. Would you please, what is the minimum wording requirement on the label, and does it need to have the word simple apparatus? Also, could it be a sticker? The label shall list manufacturer, model, serial number, etc. Yes, to answer your question, it is correct. It doesn't have to be marked with all of the EX parameters, but it would be good practice to actually word on there to say this is a simple apparatus. And you would want to mark on that label the manufacturer model serial number as well. Now, generally speaking, a simple apparatus is going to have that information, at least the manufacturer model, you know, the part number, the model number, potentially the serial number as well. If it doesn't, then you certainly want to include that on a label. And again, when you say sticker or something like that, it has to be a permanent label of some sort. So stickers
I
are
believe I
acceptable.
managed to share, right, Bob?
Yep,
I don't know
I
what's
see it.
wrong with me today. Okay, so our fourth question, you can see it, right, Bob?
Yeah, I see it.
It's basically it's a lot of questions that I compiled together. What is the difference between safety ground for electrical equipment, ground for safety barrier, signal ground, or how to connect screen and shield wires, or can we connect the ground to other ground point? You know, we have discussed this earlier, and we have prepared an answer. I'll try to go fast on it because we are running out of time. So go ahead.
Yeah. I think that pretty much explains it, but the cable screens are usually earthed at one point only, usually at the non-hazardous end. And the screen, we do want to ground it, but again, it's going to be earthed in the safe area, if you will, or the non-hazardous area. We've already talked a little bit about the difference between the clean earth and the dirty earth. So we just have to treat it. This is a good picture, if you will, that shows kind of how we would treat the screens, if you will.
Okay, next we have a question. Well, there was a missing.
Yeah.
Okay, so next is if you discussed this in the DSD, if a component of a system is IS, can we consider the whole system IS? Or how do I verify an IS circuit? And somebody recently asked, in fact, in this very webinar, which parameter to use for simple apparatus?
Right.
As we discussed, we need to have a DSD, so we need to have combine the system together.
Right. Yeah. So in just because we have an IS field device, we have to use an IS associated apparatus. We have to use whatever matches up that device in the field to make sure. So it's called our entity concept, and every device within that system, that loop, if you will have these parameters published, and these are the types of devices that will be showing up. So a simple device is basically something like a switch. It does not require certification. An IS apparatus does require certification. So things that'll basically store energy for the most part, things like transmitters, solenoid valves, those are stored energy devices. They do require certification. And then, of course, the associated apparatus, which is your intrinsically safe barriers, they do require the certification as well.
Yeah, something like this.
These
are the parameters, and this is the Excel sheet. Well, actually, it's an online tool. A lot of you guys have been asking, can we send the Excel spreadsheet? Unfortunately, with the Excel spreadsheet, the problem is that the parameters keep changing, you know, new certification and so on, and to keep it updated is a little difficult. So we have provided a tool online. You can log in online at gminternational.com, and you can see this tool, and eventually I believe you can also download it. So just use that way. So there was a live question. The answer is right here. Pros and cons of using a Zener versus galvanic barrier. We discussed that a little bit. Here is a recap.
Yeah, and the main difference, really, the Zener is the dedicated earth versus the galvanically, the not dedicated earth. Generally speaking, Zeners are a lower cost. Galvanically are usually a little bit more expensive, but as time has gone on, what we're seeing is that from a galvanic pricing has actually come down. There's much more competition, and in Zeners, and the volume is starting to increase dramatically. So.
Okay, so now what time is it? Well, it's 12 o'clock, so we have a few more minutes if you guys want to stay with us. Can an EXD enclosure have a removable gland plate? If a gland is removed from maintenance and reinstalled, does it need to be re-inspected formally?
Yeah,
Well, I
an
don't know the
EX.
answer to that, Bob.
Yeah, no. Well, gland plates are not on EXD enclosures since they are typically cast. A cast EXD enclosure is usually a sand cast or a pressure cast type. You'll find gland plates on EXE enclosures, increase safety. And of course, anytime you're doing maintenance, an EX on equipment, a detailed inspection is required. So we could be doing some preventative maintenance. We could be doing some scheduled maintenance or what have you. So we do want to update our register, our hazardous equipment register, to reflect that we've done an inspection on that piece of EX equipment.
Okay, well, after initial installation and commissioning of an IS system, what is the recommended periodicity to validate a system? What is the procedure to check an IS loop without disturbing or shutting down the process? And let me add to this question, a live question that came in, which is not, well, first you answer that, and then I will head on.
Sure. So yeah, from -17, every piece of equipment shall be inspected at least every 3 years, and it can be verified under a live condition. But the way that we're actually going to verify that loop, I mean, to do like, for example, doing resistant testing or something like that, if we're actually going to test a barrier, one of the procedure of testing a barrier is that we actually want to take it offline. We want to disconnect the barrier and check whether or not we're actually having resistance on the inside of the barrier and all that good stuff. We don't want to just take a meter to a barrier and all of a sudden we could be inducing current into that barrier during the testing. And so we don't want to do that. So there is a procedure for actually doing it.
Yeah.
As far as the time is concerned, generally, again, every 3 years, we just want to validate our system. That doesn't necessarily mean that we actually have to go and disconnect every barrier in 3 years. It does not mean that. We may just do a visual check, detail check. If there hasn't been any modifications, there's no corrosion, everything is fine, everything is operational, then just a visual close or detailed inspection without actually doing taking it out of service and checking it is perfectly acceptable.
Yeah, well, to add on to that, there is a question, and it's also a fact that the barriers are, most of the time you have SIL requirement, C requirement on this EIC 61511 or 5008, and they are to be tested on the T-proof test, so proof test interval. So it's a different issue here.
That's
and yes, a barrier, the question is, do barrier need to have proof test interval? Yes, they do. How do you check them? Well, it depends on you can read this in the safety manual, for example, depending on the efficiency of the test you're trying to do, how much of the dangerous undetected failure you're trying to detect. You can do a live test, for example, using a heart system, so you can send a heart signal to your transmitter and you verify that the feedback is correct. But as Bob mentioned, to do a 99% or 100% full proof test, you need to most likely disconnect the barrier and do a full calibration of the same. Now, how often you do that? Well, it depends on the barrier, depends on the manufacturer, depends on the design of it. It can be, our experience, between 1 and 10 years, honestly. So it's an important factor to determine how to use select a barrier. Okay, next. What are the differences between IA, IB, and AC, or the advantage or disadvantage of each one of them? Are you guys still with us? Because I'm sharing, I don't see. Yes, I can see you're still with us, and if you have time, we have some time.
Yeah, so IA is suitable for zone 0, 1, and 2. IB 1 and 2. IC is suitable for zone 2. Basically, the difference between the 3 types of protection concepts and the barriers themselves, IA equipment has basically redundancy, if you will, and IB does as well. But you can deal with 2 faults. Actually, the reason why you see that one slide that we showed, the 3 Zener diodes, that's actually an IA barrier because it has double the redundancy, if you will. IB would actually have two Zener diodes, and an IC would just have a single Zener diode. So that's basically the difference between a barrier that might be suitable for zone 0 and one that's only suitable for zone 1 or zone 2 only.
There are some other small differences, Bob, but
yeah,
the idea is if you select a barrier which is IA certified, you can be used in all the.
That is correct. That is
all
correct.
The zones or
it makes sense if you, yeah, and most of the time, what you're going to see is most of the barriers out there, especially from folks like GMI, are going to be rated for IA applications.
Okay, let's move forward. The next is, can I install a barrier in the field or in a remote area? Well, assuming that the barrier itself is certified for a classified area, typically they are. GMI barrier, most of them are certified for zone or division 2 installation. Of course, providing you provide an IP54 or better protection, because themselves, you cannot just put them in the field, like that.
Right.
But
yeah,
that can also be installed in enclosures, right?
Right.
Or
so
another method of protection.
Right, and this comes up actually where we talk about the length of cable, and you might have a 2C gas environment where that cable length is really limited. So one of the ways that you can somewhat get around it is maybe installing the barriers closer to the field device. And if you have to do that, well, again, as Paulo says, a lot of the barriers are rated for installation in the zone 2 environment, but say I need to put them in a zone 1 to be very close to a zone 0, then we could put them inside of obviously a flame-proof enclosure or potentially a purged and pressurized cabinet as well.
Next question, I think we already answered that. In which application IS can be used? We discussed that during, it was one of the poll questions. So basically all low voltage applications, 420 switches, voltage-free contact, temperature sensor, solenoid valve, small solenoid valve, strain gauges, and so on, but low power devices. Now, well, we always get this question. It's it's coming to the end of our webinar, but we do have a live question I want you to answer about. We are interested in whatever, different type of question. You can go online, GMI website, and you can see our live webinar schedule. You can also, all webinars are recorded, all my mistakes are recorded. And there's a YouTube channel, you can go back and review them. Also, at the end of the webinars, probably the next day or so, we will send you an email, follow-up email with the copies of the presentations, both presentations we used. And Bob, the question we have live is about IS and surge protector. The two can be used together as long as the surge protector are also intrinsically safe certified. They typically, if I remember correctly, do not have safety parameters. They don't store energy or not. I don't remember.
Yeah, I've got to go back and look at that. There is some documentation, or there is some stuff in there about the use of surge protectors. And I don't have the answer to that one right now.
Okay, well, we get to this answer, then we have the person there. We will send this answer along with the information.
Yeah, and there was the must have all the information, such as a word label, serial number, or is it preferred? In case there is no such information, would it pass the standard regulation, e.g. on a thermocouple, which is a simple apparatus, or merely two wires? All information may not be feasible. And that's a good point. I think if we have that type of information, we'd want to put it on a tag. But we really have to go back and look at what are the requirements in each country with regards to the inspection of intrinsic safety. And so the way we could probably best answer that is pull up the inspection charts for out of 60079-17 for intrinsic safety, and see specifically what the requirements are when we're doing an inspection. And I know one of the things is that are all the products clearly marked and labeled with all of the relevant information. So it's a very broad statement. And it's so basically, if we're saying our thermocouple, it's a simple device, we have it labeled with all of this information, that would meet the requirements.
All right, guys, we have come to our conclusion. I've already launched the poll to the Aero schedule. Done. This question is a project required? Okay, well, thank you. Thank you, Bob. Thank you for your time. Thank you for getting up early in the morning as usual. And thank you for guys for the excellent and good feedback. And the poll, stop share, no, okay, share result. Well, let me show it to you how you voted. And okay, thanks, guys. We'll talk soon. As I said, you can go online, see the next webinar schedule, and yeah, Bob, I don't know, we're on another 2 weeks.
I'm not. Yeah, I don't know. I don't know when our next one is.
Kind of space them out. You know, we were doing too close together. We have other jobs to do. You know, you have your job, I got my job, and in this COVID period, we need to get any job out there. You know, we had to fight for it. Right. Okay, guys. Thank you. Thank you again, Bob.
Yeah. Thank you, everybody. Great questions. Appreciate it. Be safe and happy holidays to everybody. So
we have some holidays coming up. Let's hope. Yes. Nice holidays. Thank you. Ciao, ciao.